Recording is rolling. It's Monday, August 29. So we're gonna solve some of these college physics problems with you guys. This is about where we left off last week. And then, yeah, I remember back on Friday, that was a short day. I could have used a regular length day because I wanted to have you guys do reaction time activity. So see if we can fit in that in today. All right, some other stuff coming up. You guys remember that let's see, this Friday, I'm going to pick up from you guys those college physics problems. It's a homework assignment. And when you guys walk in Tuesday, coming back from the upcoming 3-day weekend, because it's Labor Day, have the AP classroom assignment done, and then I want to go over those. Now, those are both linear motion and projectile motion problems. So I do want to get you guys at least started on projectile motion by the end of this week. Yeah, go ahead. These right here. Yeah. All right. So yeah, at least if I can get you guys going on, because if you've read those AP classroom questions, a lot of them are pretty conceptual in nature. AP redesigned its AP physics exam back around 2014 or so, and they did make it more conceptual. So yeah, I think you guys will be able to do those. If I don't think I've given you enough projectile information, then I might even bump this date. But for now, let's stick to that one. Oh, I'm not going to be here Wednesday. Just got appointments and stuff I got to go to. So my plan for Wednesday is to give you guys some free response questions and have you guys work on those in teams, and then I'll go over the answer keys the following day, Thursday. So these will be linear motion questions, and you can see the kinds of questions that AP would ask. Also, over this last weekend, I did write you guys' linear motion quiz. So my plan is to get that to you guys by the end of this week. And I think what I'm going to do is make that a take-home quiz. Been doing that last couple of years since the pandemic's been going, and that's actually worked out in a lot of ways. All right, so there we go. So we're looking at, let me update this attendance real fast. All right. Okay, let's solve some physics problems. Physics. Okay. All right, so for a dive into these college physics problems, let me go back and mention one that we were looking at last week, because yeah, I feel like there were some things I was trying to say that I didn't articulate that as best as I could. That it's like, okay, I was trying to make a certain point, but here, you guys remember I had you guys do the Kahoot, and this diagram explained quite a few of the answers. Okay. So if you throw a ball straight up at 30 meters per second, you could ask lots of different questions about that. You could ask what's the hang time, so what's the total time it's in the air, like going up and coming back down. You could ask what's the maximum speed, or so what's the maximum height it goes up to. You could ask what's the speed as it's crash landing back at ground level again. Okay. This is a nice problem because you can see intuitively what the answer is, even if you don't quite know the equations, but you know how things work. So you guys know that velocity tends towards the Earth 10 meters per second every passing second. So if you throw it up at 30 meters per second, the 1 second later it's going 20, and then 10, and then 0, right? It's like slowing down. Right? But then coming back down, it speeds up. So 10, 20, 30 meters per second. Right? Oh, yeah, go ahead.
Is that when you add 10 meters over a square and then going down?
Right. Yeah. So.
You're not subtracting 10 meters.
Right. It's 10 meters per second per passing second towards the Earth, right? So if it's going away from the Earth, it's slowing down. If it's going towards the Earth, it's speeding up. But it always tends towards the Earth, right? Yeah, and I like the way you said that too. It's like if you had dropped the ball, right, then it would just be like this half of it, right? That's one thing, because that's exactly one thing that I meant to say last week, is that sometimes if you take this type problem and you split it in half, the answer becomes a lot more apparent. So, for example, if you said, like, what's the maximum height of the ball, right? Well, you guys can see if you throw the ball up at 30 meters per second, it's also going to crash land at 30 meters per second. Right? So there's like some symmetry going on, right? How about this? What if you sort of figured out it would take 3 seconds to reach the top? You say, well, it would also take 3 seconds to fall back down, right? You might use this equation: final velocity equals initial velocity plus AT. let's say you look at the first half of this. You want to say like, how much time does it take to go from here to here? Right, so I know it's going to 0 meters per second at the top, coming from positive 30 meters per second. If you consider positive to be the upward direction, right? So now we've defined a direction, right? Which means that acceleration is actually what number exactly goes here? -10, because see, if I've defined upward as positive, then gravity must be pulling the other way, right? Then times some amount of time. Okay. If I call this -30, this could be +10. Okay, they have opposite sign. Okay. So 2 algebra steps: subtract 30, divide by 10, right? And then the units work out. It's going to be, you guys can see, it's going to be 3 seconds, right? But that's only to go from the ground to the top. But then by symmetry, you guys can say, well, going from the top back to the bottom would also be 3 seconds. You guys get it? Okay. What about how fast it's going? Okay. So I want to solve this 2 ways. One is the complete way, and the other is to split this problem in half, because you can see like different advantages. How fast it's going. So you could say final velocity equals initial velocity plus AT. No, it's the exact same formula, right? You guys see it's the same formula. Then I'm gonna change the final condition. See, the one I just did, I did from the ground to the top. But what I'm about to do is go from the ground back to the ground. So I'm gonna have this guy be 30 meters per second. Upwards, we call it positive. This will still be -10 meters per second squared. Okay. But how much time would it take to get back to the ground?
6 seconds.
6 seconds. You guys see, because 3 up, 3 down, right? You say, okay, symmetry takes 3 up, it'll take another 3 to get down, so 3, 3, 6. Right? I wonder how fast it's going to be crash landing. Now you guys know the answer already, right? Like this is the magnitude, and it should come out negative because it's down. Okay, that's good. All right, so let's try this out. This time that's -60 plus 30. And notice the units work out too. Meters per second squared times seconds would be meters per second. Can you add meters per second to meters per second? In fact, if you're adding or subtracting values, they have to have the same unit, right? You can't add gallons to miles. That would make sense, right? So meters per second, that does in fact give you -30 meters per second, right? But you could have solved this the other way. You could have said, like split this problem in half, say, hey, what if I just dropped it from rest and it just had been falling for 3 seconds? Okay? So you could have done something like this. Final velocity equals initial velocity plus acceleration times time. You know, there's the formula a third time. But if you drop it, then this would be 0 meters per second. Okay. Let's call it down negative just to be consistent with what I've been doing all morning. -10 meters per second per passing second times, and you know, it would be 3 seconds just for the falling half the trip. You guys see that still gives you the same answer, right? It's the same answer, just a little bit different way of approaching it. Okay. And finally, what if you ask the maximum height question? Okay. Now, last week, the way I solved it was to go from the throwing point to the maximum point. You could say x equals b naught t plus 1/2 at squared. You say, well, let's say you figure out that it take 3 seconds to get up there, because we figured that out from this, right? It takes 3 seconds to get up. So now this, I'll do like 2 ways, right? So the sort of longer way to figure out maximum height is to do, I threw it at, let's say positive 30 meters per second. Let's let it go for 3 seconds and see how far it goes. Okay. Gravity's still playing the opposite way, 10 meters per second squared, pop in 3 seconds. Okay, don't forget to square this because we're solving for displacement now, right? Okay. So what's 30 times 3 plus 1/2 times -10 times 3 squared? Okay. Now, you guys already know the answer to this from last week. If you throw anything upwards at 30 meters per second, there you go. Oh, okay. You guys remember what we got? Oh, it looks like actually here I used a different formula and I got 45 meters, right? Right. So see the way I solved it here before is to skip through time. Right. So notice that the 3 seconds you didn't have to solve for first. You just say, well, it goes to 0 from 30. Okay, got 45 meters. This should come out to 45 meters, right? If it doesn't, something's wrong. 45 meters. 45 meters. Okay. So there's actually 2 ways to solve 45 meters, right? There's what you're seeing right here, going through time. And then there's the original, well, way I have it from last week, where I just used that third kinematic formula. Okay. But another way you could do it is you could split this problem in half and say, hey, wouldn't that also be the same as the falling distance, just the opposite direction? Instead of going up 45 meters, it would have to go down the same distance. So you could solve for 3 seconds, right? And that would look a little bit different. Actually, be a little easier to solve because you could just take this kinematic formula and you could simplify it. Because guys, if you drop anything from rest, then what is initial velocity?
0.
0. So doesn't it just boil down to 1/2 at squared? Okay, so just more simply, it's just 1/2 at squared. Okay, now this is only true at initial velocity is 0. Right? Okay, but I should get this 45 meters. But let's see if I do 1/2. Let's be strict about the sign convention. I'm calling down negative, right? So I've been calling down negative all morning. So let me stick with that. That's 3 seconds squared. See, 3 squared is 9. Half of 10 is 5. What's 5 times 9? 45. And notice it's still negative, right? This negative sign comes out. Negative 45 meters. Okay. Now, why does this one come up negative when all along it's been positive? Well, because I changed the framing of the question slightly. Okay. In this setup, the math is leading to like, if you throw it from ground level, how high does it go? Oh, well, it went upwards 45 meters, and I've been calling up positive all morning. Okay. But in this new framing of the question, I'm saying, well, what if you looked at the second half of the problem? What if you had dropped it from this height? How far would it fall in 3 seconds? Because that would also answer the question, but it's downward. Hey, you guys see that? Okay. So yeah, because displacement is a vector value, right? Displacement, right? Vector value. So positive negative signs matter. Right, you guys get that? Actually, that's a pretty good warm up for this morning, right? So take something that you guys have seen before, and there are lots of ways you can approach it. I could throw you guys a question, and I could have 5 different students approach it like 5 different ways, and all, as long as you're getting the same answer, all these different methods will converge to something like that. Right. Let's take a look at this page. Any questions so far? You guys doing all right? All right, so I wanted to give you guys a little help on number. Oh yeah, go ahead. Oh, yep, that's exactly the one I was going to bring. Yeah. So which question on 20? Part B. Distance travel.
Like the distance of the interval and the distance of the interval and add those 2 distances together, or just plug the number. Just plug the number.
Yeah. There's 2 ways you could approach this, and again, they should lead to the same thing. So there's a graphical way to approach this, and there's also an equation way to approach this. Right. So I don't want to solve this whole thing for you, but I do want to set this up to show you like how to solve it. And let me take you through both of those approaches. Because notice on number 20 they give you an acceleration versus time diagram. We got to do that. Number 20. You guys remember those 3 graphs you've been making over and over again? Okay. So let's try that. X versus t, b versus t, a versus t. Now the a versus t, I'm going to make a sideways t just because I kind of know where this problem's going. So displacement versus time. This could be in meters and seconds. We got velocity versus time, meters per second, seconds, and acceleration versus time. This would be meters per second squared, seconds. Okay. I mean, you guys have seen the set of graphs a number of times now, right? Okay. And what they give you is this very last one. Now I'm just going to copy paste the graph shape without the numbers, and I bet you guys can figure out the numbers. You guys can place the numbers in here, right? Okay. So they said you've been accelerating for like some time. Okay, and then bam, suddenly the acceleration drops to 0. Hey guys, is 0 acceleration the same thing as 0 velocity?
No.
You guys are right. It's not. So you can still be in motion. You can still be in motion. You're just not changing what you're doing, right? Just like cruise control. Okay. And then what they do? Okay. Good. This my graph shape looks a little different than theirs, but you guys get the idea. Okay. They did something like this. Okay. Notice that the acceleration is like constant values, right? It's either a positive constant value or it's 0 or it's a negative constant value, and it like jumps. Right? In fact, in a math class, they might just like show this as a jump, right? Or in physics, if you had an accelerometer, right? then this might just be a very, very steep lines. Okay, very steep lines like this, right? Okay. Okay. All right, so you've got these three constant values for acceleration. This positive value, the zero value, and this negative value. Okay. All right. Didn't draw exactly the scale how they have it, but pretty close, right? All right. Now, there are two questions. There's a part A and a part B. Part A says something about velocity, and part B says something about how far has what was it, a particle moving, something like that. Okay. So now, if you start from rest, they'd have to specify that too, because could possibly have been in motion, which would throw this off. But if you start at rest, then they're sort of giving you this point. At time zero, it's zero velocity. Okay. Then what? Well, this is what's the calculus process called, going from acceleration to velocity? Integration, right? Now, integration, it's like, you guys remember you're like adding up this rectangle from left to right, because meters per second squared times seconds. What is meters per second squared times seconds? Is that meters per second? So remember how the area of this rectangle describes like a change of velocity, right? Oh, let's see. During the first like little skinny rectangle, maybe you went up to like here, and then the next same interval of time you add the same amount of velocity, and then this little skinny interval of time you have the same amount of velocity, and then this one. You guys see in equal time intervals you're adding an equal amount change of velocity. So this is going to go up like this. Okay. Or if you went the opposite process, if you started with that v versus t curve, which is increasing at a constant rate, and you took that slope, the slope of v versus t tells you the coordinate of a versus t. You guys see this rise over run is constant, just like the acceleration is constant. Okay, you guys remember that? Okay. Now, before the notes, I went from the v versus t graph to the a versus t graph. Now we're doing it backwards, but you can go back and forth. Okay, check your work. Okay. Then what about during the zero? Let's get this up to it's exactly aligned. Okay. What about when you get to zero acceleration? Okay. What does the v versus t curve look like? Is it just constant velocity? Okay. That would go like that, right? Okay. Zero acceleration, you're in motion, just at a constant rate, constant speed. Okay. And then what about this negative acceleration bit? What does that mean velocity is doing? Decelerating, yeah, like slowing down. Okay. So it's like a negative acceleration. Yeah, we got like slowing down. Okay. And this, how the numbers work out, like if I plugged in the numbers, got exactly, it does. Well, I guess I'm kind of giving away part of the answer, because at the end of this time interval, there is still motion, but it doesn't go to zero speed exactly. Okay. Okay, you guys okay with that? Okay. And then what about displacement? Right? How do you translate this to like some kind of displacement? Okay. Well, during the constant acceleration bit, during that first interval of time, let's put here, I need to give you guys at least 1 point. So time zero, let's call it position zero. Okay. So this first leg of the trip, what is this? What shape does this make? Parabola. In fact, if you start at zero velocity, what property of the parabola also starts at time zero? The vertex. Yeah. So it's just gonna be like a parabola bit like that. Do a little parabola. Okay. Now there's a reason I made it kind of shallow, because here it's gonna connect it to the second interval. Okay. So what about the constant velocity part? What do you think this graph is gonna look like? You know what? Give you guys a head start. See if you guys can get your notes, and if you get it wrong, you just erase it. See if you guys can draw that second interval for what's going on with displacement versus time. Okay. So I'm driving in my car, cruise control, just like 30 miles an hour, 30 miles an hour, 30 miles an hour. Okay. So the speedometer is pointing at the same number. There's zero acceleration. You feel just like you feel in this room. You just like as if you were at rest. You can't tell the difference from a physics point of view. Okay. And hey, doesn't that mean you are acquiring displacement at a constant rate? And wouldn't that be like, is that what you guys just drew? You guys just drew that, right? Okay. And if you got it exactly right, now this is a little tricky, but do you guys see how there's like a smooth transition from this parabola to this to the straight segment? No, it isn't jarring. It doesn't like, there's no like corners, just very smooth. Okay. You said, So that's a little tricky to get exactly right, but do like that. Okay. And then, hey, what about this last leg of the trip, where you don't quite come to rest, but you're definitely slowing down? Okay. What does that look like on X versus T? Let's see, you're still, hey, are you still moving forward? Yeah, you're still going forward. Just you're tapping the brake, you're going slower, slower, slower. So are you accumulating distance at a slower and slower rate? And what shape is that going to be? Parabola. In fact, isn't it going to be kind of like this guy, kind of hooked down? Ah, right. So like that. Okay. And I know it doesn't quite reach the vertex because this doesn't quite go to zero velocity. Okay. You guys think you could take the book numbers and then apply the numbers and figure out, well, oh, here's another way you can figure out this out too, the final displacement. Could you take, guys, what property of V versus T tells you displacement? Yeah, okay, meters. And how do you get to meters? If you have meters per second, yeah, time seconds, right? Meters per second, time seconds, which means it's something to do with the area under this curve. So I see a nice triangle here, 1/2 base height. I see a nice looking rectangle right here, base times height. And then there's like this weird trapezoid. Could you split the trapezoid into a little tiny triangle plus a little tiny rectangle, add those bits together and get the total displacement? So that should tell you the difference from here to here, right? That would be the total displacement. Okay. Is that right? Okay. So here, so this whole weird shape, I might call delta x, like a change in location, like or displacement. Sometimes I say x or displacement times delta x, right? And then here, this would also be your delta x, like your change in location. Okay. All right, any questions on that one? Okay. Now, so the other way you could do this would be to set up equations. So number 20, part A had to do with something about velocity. So I could go final velocity equals initial velocity plus acceleration times time. Okay. Now, the starting off velocity was 0, right? Okay. So you can start 0. They gave you some positive acceleration for some interval of time. You could figure out what it is up to there. Okay. Then the second interval of time, there was 0 acceleration. So that means that velocity just wasn't changing. Okay. So I guess you could kind of skip over that. And then you can bring this equation back again. Except now you plug in the previous final velocity now feeds into the initial velocity. And now you plug in a negative acceleration for the last interval of time, which should just be like this little interval of time right here. Okay, boom, boom. And then you could get how fast it's going. Okay, so first you need to figure out how fast is this point right here. So you do initial velocity 0 plus acceleration is the slope of this line times this amount of time t. Right? That'll bring you up to, I might call it well, VF, but just for the first segment, right? Okay. Then you have that number. That becomes the initial velocity for, well, the next segments. Actually, it doesn't even change for the second segment, so you can just kind of skip over that. Right. See, like this little bit right here. It's still like y equals mx plus b, but you start with this velocity, and then you have some negative acceleration, like for some like this time interval. Okay, here maybe I'll do this. Call this t1, t2, t3. I'll call this vf1. You call this point down here vf3. Okay, so final velocity after the third interval. So this would be vf1, and that would be also this. This would be a vf3. So vf1. I call this a1, and a3. A3. We call this T1 and T3. Okay. Okay. Guys got that? Okay. So I'm just trying to give you guys the big picture roadmap. Hopefully you could figure this out. Okay? And as you guys are plugging in the numbers, I want you to also be able to like see the forest for the trees. This is like the forest point of view, right? Okay. Then part B said, well, how far does this go? Like you're solving for this whole delta x. Okay, see, this is also going to be in 3 stages. Okay. So we're gonna go x equals v naught t. Here, maybe I'll call this x1. Let's call this x1. Call this x2. Call this x3. Just like this is t1, t2, t3, right? Okay. Right, so we got v naught t plus 1/2 a t squared. Okay. Now, if you start from left, the bit gonna go away. Okay. Then x2 is going to be, well, actually starts in motion, doesn't it? Right, you're already in motion here. Hey, isn't this x2 just constant velocity? So wouldn't it be some version of speed times time? Okay, it's going to be second time interval, and this is vf1. So this also feeds in right there. Right, the speed you build up to at the end of interval 1 is the speed it's going during interval 2. Right? And then the third bit, we're back to v naught t plus 1/2 at squared. But let's think about what bits would be what. Okay. Now, remember, it's during interval 2, it's just one constant velocity. So that by the time you start the third interval, you are also moving at that velocity. The velocity at the end of interval 1 is the same as the velocity at the start of interval 3. You guys see that? Okay. Which what I'm trying to get at is that this number also feeds in here, just like that. Okay. This is the third acceleration, which is a negative value, and this is the third time interval. So here, I'll even make it up. That's a negative value on that last acceleration. Okay. So there you go. There's like the forest roadmap for how to solve that. The equations, the graphs, right, different ways you could approach that. Right, you guys good there? All right.
So we would
Yeah.
add each of the distance.
Right. Yeah. Okay. So x1, x2, x3. Right. So they'll all be positive values, right? Positive, positive, positive. Now on this x3, you're adding 2 bits together, one that is positive, one is negative, but overall it's going to be a positive value because it's like this kind of curving down sort of parabola. I call it like concave down. Okay. Okay. So this little bit will be a negative number, but positive, positive, positive.
Okay, so we can't just plug in, we can't just plug in one for the equation, right? Because that wouldn't give you.
Oh yeah, the whole thing was like 20 seconds long. Right. Yeah, you have to break it down into 3 bits and then solve each one because they each have their own unique acceleration. All right. Right. Moving on. But so next one I look at is ooh. All right, this one I like a lot. Okay, number 35 we're going to be looking at. It says Speedy Sue. Guess we're following. So I remember last week there was a problem we solved that was it involved no acceleration, it was just distance equals speed times time, or some version of, I should say displacement is velocity times time. But I remember something with like a system of equations that like there was it was a complex question, is what I'm trying to say, right? You had to think big picture and how these equations would interact with each other, right? Beyond just the basic, like, oh, okay, I have 3 of these 5 variables, therefore I can solve anything I want, which is kind of a lower level application of this. And so number 35, Speedy Sue question is one of these type questions. It involves putting together a lot of bits. You have to understand equations, you have to understand complex relationships. There's even going to be a quadratic formula that pops up in this one. Well, that's how I'm going to solve it anyway. Okay, we got Speedy Sue driving at 30 meters per second, which I think I looked at last week was about 67 miles an hour. Okay. Enters a 1-lane tunnel. She then observes a slow-moving van this distance ahead of her, 155 meters ahead of her, traveling at 5 meters per second. Oh, that's way slower, isn't it? That's a slow-moving van. She slams on the brakes, but can only accelerate at -2 meters per second squared because the road is wet, which is true. Guys, what is Earth gravity again? Yeah. Okay, there you go. So magnitude's 10 meters per second squared, right, and that'd be vertical. Now she's accelerating horizontally at well, 2 meters per second squared backward, right? Did you guys ever hear like a G force, pair of G's? Right. So how many gravities are we in right now? One, right? So she's in two meters per second squared magnitude. Right? How many G's does she feel?
1/5.
1/5. Yeah, it's like a fifth of a G, right? I'm just talking about the horizontal motion, right? I'm ignoring the vertical stuff. Okay. Yeah. So she feels thrown forward, almost as there's like a fifth of Earth gravity, like pulling her forward relative to the car, right? Because you slam on the brakes, you feel like you're thrown forward, right? Okay. Just give you guys a little context here, right? Okay. Now, if the road had been dry and she had new tires, then I can tell you what the ideal acceleration is, because I just remember this from traffic classes back in college. It actually is pretty close to 1G, right? So if you have brand new tires, dry road, you can get up to, you can actually get a little over 1G, like 11 meters per second squared. Okay, so the road is definitely wet. That's kind of cool they mentioned that detail. Think about how this works. Okay, will there be a collision? State how you will decide, and if yes, then how far into the tunnel and at what time does this occur? How far? That's like a displacement in meters, and at what time, t in seconds? They're asking you to solve for two variables, which is kind of a hint as to what's about to happen, which is we're going to set up a system of equations, because if you're solving for two unknowns, you probably have to have two independent equations. Hey, maybe an equation for her motion slowing down, and also an equation for the van that's probably oblivious to the whole situation, just like slow poking along at constant velocity. Ooh, right? I think we do a system of equations. Right? And if the crash doesn't happen, then how close will they get? Maybe like maybe it'd be like a near miss. Right? All right, so let's try this out. Speedy Sue. Okay. I do like to start with pictures. I like pictures, so I know everybody's brain works different. So let's get a picture anyway. Picture time. Okay. So here's Speedy Sue. Maybe I should do. Okay. I know. S is for Sue and V is for van, but S looks like a 5 and V stands for velocity also. So maybe I'll just call Sue like car A. Is that okay? Sue is car A. And then I got this van up here that I could just like call like vehicle B. Okay, is that all right? Just the letters aren't like all wacky. Okay. So let me draw a there's two vectors that I care about for car A, which is Sue. Right? I care about her velocity and also her acceleration, which are different kinds of vectors. Okay. So the initial velocity of car A is, they gave us a number. Yeah, thank you, 30 meters per second. Okay. Now there's also a backwards acceleration on her, which is a different kind of vector. Maybe just to distinguish it, I'll use like a little fat arrow. And this like acceleration is, okay, 2 meters per second squared. All right. I'm pointing it backwards. The way I wrote it is actually the way you want to do it. If you point it backwards, you could indicate with the positive value. Just because I know we're going to dive into the math, I'll go ahead and slap on the negative because mathematically it's a negative value. Right. Then the van here has a real slow forward velocity. I'll call velocity of vehicle B is 5 meters per second. Okay. Notice your book gave you all values of 3 significant figures. You guys see how every number has 3 sig figs? Okay. So just for the notes, to make the notes a little cleaner, I'm just going to boil it down to the numbers that we need. But you guys know these are all 3 sig fig numbers. Right? Okay. Now, one more thing. I know that the distance between these two guys, the distance, I'll go from the front of her car to the back of the van. That's why I'll trip for this, because that's what would crash, right? Okay. I'm going to label that D, because that can be like a constant value. I mean, well, that's going to change, but that was the starting value anyway. Okay. That was 155 meters. Okay. Now, supposing they crash, I'm going to start off by assuming that they do, and then if I get like impossible equations, I'll say, okay, well, I guess they didn't, and then resolve from there. Let's say the crash happens like down here. And that I will call distance x. Because like we're solving for x, and we're also solving for t, right? How much time does that take? Okay. Can you guys set up a system of equations before I do? Set up an equation for vehicle A and also for vehicle B. So for Sue's car and also for the slow van. Set up a system of equations. You guys know you're using that green poster, which looks like this, as your formulas so you can set up some models, right? All right, so if you can't stay a step ahead of me, then please do. Right, so really just trying to give you guys a head start. Okay. So I'm going to go for, let's say it's for Sue's vehicle A. I'll go x equals, here, let me start with the models. Okay. V naught sub A times some amount t. I could say plus 1/2 at squared. I'm going to go ahead and just include the negative sign at this point. Minus 1/2 at squared. Okay. So, you know what? Okay, the fact that I'm going to embed this negative right here, let me go back and make my picture actually like correct to how I drew it. So I drew the vector in the opposite direction. Okay. So it's 2 in the left direction, right? And I'm already embedding the negative sign right here. Okay. Okay. So the magnitude 2 is just going to be in here. Okay. Now that's for the car. Okay. Then we got the van. Now the van. Now there's different ways you can set this up. I won't tell you both of them, but I'll just stick to one as I draw this. Okay. You guys see this distance right here? What could you call that? That'll be the distance the van actually travels, right? Is that x minus d? I say that's x minus d, right? So, okay, so x minus d is equal to the speed of the van times also some amount of time t. Okay. Let me go back to this first equation. Let me modify this. I know I said x sub a for speed of the car, but that really is just this x, right? So I don't even have to put subscript a because I could just call it x. Okay. So this is like a system of formulas that should solve the whole thing. Okay. Where, guys, is this x the same x? Yep, same x, because x minus d is the distance the van goes to the collision. Okay. Is this t and this t and this t all the same t? Yeah. So this is where like they would collide. Okay, so we're gonna set this up assuming they do collide, and let's see what happens. Okay, so if we get a positive values for this distance of time, then all works out. All right, so I'm gonna take these and just start plugging in what I know. Right? I mean, I don't know this x, and I don't know this t, but I should have numbers for everything else, right? Oh, okay. Pause right here before I get going too far, because the other way you could have approached this is you could have said that the position of the van, you could have just taken this d and added it over. You could have said x equals v sub b times t plus d. You guys see that? You can just take this d and add it over. Oh, yeah, thank you. And the interpretation of that would be in terms of locations, which is actually how, thank you, actually how AP writes their own equations. Okay. You guys remember, here, let me point this out real fast. Okay. You guys remember these 3 kinematic equations are the same ones as on that green poster? But let me go ahead and point out how AP does them a little different. first they switch the order of them a little bit. Right? You guys see how final velocity equals initial velocity plus a times t. Right? But they threw in subscripts x, so they're saying along one particular axis. Now sub x could be sub y or sub z or sub sub w. It could just be any axis. So I think they're getting a little too granular, but right, that's why I simplified them a little bit. Right? Right. Then what they listed second, I listed first. Right. So notice how theirs is different from mine. The main difference is see final position equals initial position plus, and then they go to b naught t plus half at squared. Right. So the way I put it on my own poster is this is really displacement the way I wrote it, right? But they're saying final position equals initial position plus. But if you subtract over x naught, it'd just be x minus x naught, which would be displacement. Okay, so that's like my simplified version. Okay, yeah.
So is your version like the delta x?
Yeah, you could even do that. You could just call this delta x, right? Like a change in position. So change in position, displacement. Okay. Okay. Different textbooks, you see them a little different. Okay. Okay. And then the last one, I think okay, so instead of see where I put x here, they said the change of position, right? And they also include the subscripts, like for to specify an axis. Okay. So I'm just pointing out little technical different ways to write these equations. Right? It's a little bit different interpretation, but they're like the same theory equations, right? Okay. So just when you guys are using that as a reference page, you say, okay, hey, that is a little different, but I see how it all lines up. Right. Okay, so back to here. Let's pop in the numbers that we know. So we make a system of equations. We got 30 meters per second for some time minus 1/2 times 2 meters per second squared times time squared. Okay. Now this is where if you put -2 there, you just put a plus here. So I just already include the negative there. Okay. Okay. And then for the hey, let me go ahead and just take this d and add it over. Is that okay? Just take this d and add it over. So wouldn't that be x for the van equals 5 meters per second times t I should say plus d, and d is given as 155 meters. So this is my system of equations. Okay. Now, if you got this far, then you've successfully been able to like see the big picture, think critically about how to put the system of equations together, and also navigate those kinematic equations. Right? Everything beyond this is just algebra. Okay? You guys get that? Okay. So if you're good at algebra, then you're definitely good from here on out. Here, let's go ahead and solve this with the guys. There's different ways to solve systems of equations. Hey guys, if x is equal to this top line and x is also equal to this bottom line, can I just take these two and set them equal to each other? They're both x, right? And then we can solve for t. All right, let's try that. Let's try that. So we're going to go 30 t. Hey, 1/2 times 2. Ooh, I bet that's why they gave us 2 meters per second squared, because that very simply goes over. Minus t squared is equal to 5 t plus 155. Of course, all these numbers have units on them. Because we're saying x is equal to x. That's why I can say that, right? For the preceding line is x is equal to x. And then it leads straight down to that. Okay. Who has a question so far? All right. Hey, do you see a t squared and also a t and also a constant value? That means this is going to feed into what ultimately? The quadratic. Quadratic equation. It's going to be quadratic. Okay. So maybe I'll do this. Let's add the t squared over, get t squared, subtract the 30t over. That'd be minus 25 t squared, or sorry, just t, minus 25t. Then plus 155 equals 0. Okay. Of course, all those numbers have units on them. Is that right? Okay. T equals -b plus or minus square root of b squared minus 4AC all divided by 2A. Okay. Just for a second. All right. Yeah. Just for okay. All right. So what is this? 25. Okay. Well, I got a plus or minus, so let me start with the plus. This on first. 25 plus the square root of 625 minus 4 by 1 by 155. Whoops, square root. Okay. What just happened? Start over. Okay. 25 plus square root 625 minus 4 by 155 all over 2. All right. Okay, so I'm getting time is equal to 13.6 seconds. Okay. Does it seem reasonable? Well, see if you're going highway speed and you're having a lot of trouble slowing down because the road's wet, maybe. Okay. Now if I go back and slap in a negative sign, let's see, or or 11.38 seconds. What was the plus? What brand really? 13.6162 seconds. Okay. Okay. Actually, I think we're good because here, both these numbers look all right, right? Let's imagine that these are not cars, but they're particles because all these equations are kind of like having particles floating around. Okay. So the van's just poking along and the car is like screeching, but slowly just stop. Right. Do you imagine that these two particles could go like, right? If they just stayed independent of each other, they could like goes through each other. Is that okay? In fact, if they goes through each other, then they will cross paths twice. I see cross paths twice. Which one of these refers to the collision moment? The smaller time, right? The smaller time is the collision moment. Right? Now, if you want to check your work, you can take 11.38 seconds. Let's do that. And plug it into each of these equations. I know I'm short on time here, so say x equals. Okay. Let's try it out. So what's 5 times 11.38 plus 155? So for the van, it's at 211.9 meters. And for the car, what's 30 times 11.38 minus 1/2 times 2 times 11.38 squared? That is also 211.9 meters. Right. So there you go. You got the time of the collision and also the position of the collision. Boom and boom. Okay. Okay, so that was a nice complex problem there. Yeah, have to know the concepts and see the big picture and apply the equations to get it all completely correct. All right. See you guys tomorrow. In the recording.